Don't let the 1 microamp reading fool you. This board isn't off. It's Green Pill Nano in its deep sleep state. Green Pill Nano is a drop-in replacement for Arduino Nano, optimized for low power and real debugging. It is built using an STM32L072 microcontroller. Let's discuss about deep sleep mode, or also called stop mode in STM32 language. First, it allows an ultra low static current, so basically we get 1 microamp and below. It has a full RAM and register retention, which means the content of the RAM variables and also the configuration register for peripherals are retained during a sleep mode. Context resumption, so it doesn't reboot. After the wake up, it continues the code where it left off. It allows various wake-up sources, like real-time clock, external interrupts on pins, UART, I2C, and other peripherals. And it shows a very fast wake-up latency. It's in the range of microseconds. I created a demo application for deep sleep mode. You can get it from my GitHub page, github.com/linmcu. It uses RTC for periodic wake-up and a button or as a signal on a digital pin for an on-demand wake-up. It is based on Arduino framework for STM32 and the STM libraries for low power and RTC. I also wrote many parts in STM32 HAL. The beauty is that you can combine Arduino with HAL. You can use the libraries already written for many sensors and displays, and at the same time leverage the full power of STM32 by using the HAL functions. The principles and code are applicable to many STM32 microcontrollers. I will emphasize the most important points during the code walkthrough. Let's go quickly through the code and see how we need to set up to achieve those very low power numbers. If we go to in the setup function, if we go to setup board, that's a helper function that I wrote. Mainly it disables the hardware debug unit in the microcontroller to save power. Except if we compile in debug mode, these are activated so that we can debug in low power modes. Also important, we enable ultra low power and we enable fast wake up. Also another power optimization, we enable the flash sleep power down. Getting back, disable GPIO. This is one of the most important topics in achieving very low currents in low power. The idea is that the input pins have some leakage currents unless they are set as analog and also without any pull-ups or pull-downs. We here enable the peripheral clocks so that we can set the pins. We set them as analog, no pulse. We select all the pins from the ports and we apply this setting to all the ports except port A. Why except port A? Because if we want to debug, we actually need to leave pins 13 and 14 in their default state, which is serial wire debugging. If we are not in debug mode, we actually apply the same settings for the GPIO port. At the end, we disable all the peripheral clocks for the ports, also to save power. Next, another important optimization is to disable the peripherals. So any unused peripheral should be disabled. This is done by actually disabling the peripheral clock. And you can see here there is a number of peripherals listed. You should adjust that to the list of peripherals that you are using. Disable real-time clock. So we also disable the low-speed external oscillator. The board is including an external crystal for 32768 Hertz. And the RTC, if you use it, it's advisable to actually use that crystal both for precision and for low power consumption. We have here the set RTC function if we want to use the RTC. And in this demo, I want to be able to wake up the microcontroller in two ways. I want to have a periodic wake up using the RTC, and also I want to be able to wake it up if I press a button. So in order to set up the wake up on a button interrupt, I chose pin number 3. It's set up here, which is also in that case PA1. Okay, we set to be the input pin and to have a pull-up. And we connect the button between the pin and the ground. We attach the interrupt and we specify the pin. We specify a callback function that is going to be called immediately when the pin triggers the interrupt. And we specify here that it's on the falling edge. Given that we set it up with a pull-up, basically the pin is connected to the plus VCC, and when the button is pressed, basically it's gonna transition to low. That's why we set here on the falling edge as interrupt. Next, we initialize the low power, and in order to also enable interrupt from RTC, we use this function enable wake up from, and we specify RTC. Alarm match is a callback that is called when the alarm is triggered, and the sleep duration is the duration that is passed to this function and will be later used to set the next alarm. And we set the first alarm, the current time plus sleep duration. Let's look now in button ISR. So basically when the button is pressed, we just set a Boolean flag to true. When the alarm match is called, so when the alarm triggers the wake up, basically we calculate the next time for the next alarm to trigger. In the loop function, things are much simpler. So basically we test if the button was pressed, we just do 2 short blinks followed by a 1 second pause. If the RTC triggered the wake from sleep, we have only 1 blink and of a longer duration. In the end, we also set the LED pin to input analog to save power. We reset the button press flag and we enter deep sleep. What is also important is that at the exit from deep sleep, which is gonna be the next line here, we have to clear the wake up flag. This is also important for low power optimization. As I showed in the video in beginning, using RTC for wake up and using a button, we got to 1 microamp sleep current. Let's see now what happens if we disable RTC and we leave the wake up to be done only by the button. So we comment these lines, we build and we transfer. And we get to even a lower current, we get below half of microamp. Using Power Profiler Kit 2, we get the same result of half of microamp. And we can measure now, and we see the average is 0.5. Thanks for watching. I open sourced the whole project. You can find the schematics on my GitHub page, and the board is available to order from PCBWay. You can find the links in my bio.